Finding relative max and mins and saddle points of functions of two variables is a little bit more complicated than finding them for a function of a single variable, but still certainly very doable. So how do we find a maximum, minimum, or saddle point of a function of two variables? So I've got a couple of graphs here, and we're going to kind of attack it in the same way in that we're going to look for some first derivatives, some first partials, and find out where they're zero, and then kind of use something equivalent to the second derivative test to look for kind of a concavity to determine then if they're a minimum, a maximum, or a saddle point. So, for example, this sort of parabolic cone shape here, we notice that if we take the derivative with respect to x, we keep y constant. Basically, you end up, this point down here at the bottom is a minimum, right? And the tangent lines in both the x and the y direction in the plane are zero. Now, on the other hand, we have a graph over here that kind of has a weird point, kind of right about there, that here in part of the graph, you can see if we took a cross section, it would be a minimum, but if we look at it from this perspective, right, it would actually be a maximum. So we get what's called a saddle point in that case. It kind of looks like something you would put on a horse and ride, right? It has a saddle, a place where you could sort of sit in it. So how do we tell which one of these we have? Because in this case, we have, right, a derivative going one way for the x variable and a derivative going the other way for the y variable. Again, that we kind of have this horizontal tangent thing going on. So how do you tell which one that you have? So there's essentially a test. There are some steps that we're going to take. So the steps for finding the relative maximum or relative minimum in saddle points of a function of two variables is the following. So the first step is we need to find the first partials and then 3 of the 4 second partials. So we need to find the first partials, f sub x, f sub y, so the partial with respect to x, the partial with respect to y, and then we need to find these three partials. So the second partial with respect to x, the second partial with respect to y, and then the mixed second partial. So partial with respect to x and then y. And what we're going to do with these is kind of like a combination of a first derivative test and a second derivative test combined. So the first part is very similar to what we did in performing the first derivative test and finding critical values. There we were just finding the critical values of the derivative, but here we have 2 first partials, right? So you have to kind of treat this as a system of equations and find a solution there. So you might have to review a little bit of your algebra there and talk about finding the solution to a system of equations by either the elimination method or the substitution method. And so then let's assume that we have a solution. We have the point AB is a solution, and there may be more than one. We may actually find that there are a couple of points that are that satisfy that system of equations. But let's say that AB is one of them. Then we're going to compute what we call D. So D of AB. And D of AB is all about the second partials. So the second partial with respect to x times the second partial with respect to y minus the mixed second partial squared. Right? And so there are basically 3 possibilities we're going to look at for D. First, D is negative. If D is negative, then we have a saddle point at AB. Okay, so if the result of D, and plugging in our solution into D, gives us a negative number, we have a saddle point. If D is positive, then we either have a max or a min. So we have a maximum if the second partial with respect to x is negative, and we have a minimum if the second partial is positive. Okay? So D being greater than 0 doesn't tell me whether I have a max or a min. I have to then look at the second partial with respect to x. And if that is negative, so kind of think of second derivative, negative means concave down, and that means I have a maximum. And if the second partial with respect to x is positive, then think concave up, and then we have a relative minimum. And if we end up with 0 as our output, then it turns out that this test that we're doing is not applicable for the function that we have. And pretty much that's not going to be the case in the problems that we have, but it is a possibility. Okay, so let's do some examples. So the first one is we're going to look for the relative maximum and minimum points. And if there are any saddle points, we'll find those along the way too, because it's obvious from the result of D. If D is negative, then we have a saddle point, right? Okay, so let's go ahead and find our partials. So first one is the partial with respect to x. Okay, so x is our variable of interest, y is treated as a constant. So the derivative of x squared with respect to x is 2x. The derivative of x times y with respect to x is going to be 1 times y. Y is treated as a constant, so that's just y. The derivative of y squared with respect to x is 0 because it doesn't have x in it. It doesn't vary with respect to x, so its derivative is 0. And then minus the derivative of 3x, which is just going to be 3. So that's the partial with respect to x. The partial with respect to y is going to be, let's see, derivative of x squared with respect to y is 0, plus the derivative of x times y, so x is the constant multiple, times the derivative of y, which is 1, so x times 1 is just x, plus the derivative of y squared is 2y, and then minus the derivative of 3x. Well, it doesn't have a y in it, so it doesn't vary with respect to y, so that means it's constant, means its derivative is 0. All right, then we also need the second partials with respect to x and y. So let's calculate up those. So fxx. Derivative of 2x with respect to x is 2. The derivative of y with respect to x is 0. The derivative of 3 with respect to x is 0. So that second partial is just 2. All right, the next one is fyy. So the derivative of x with respect to y is 0, plus the derivative of 2y with respect to y is 2. And then don't forget we also need the mixed partial fxy. So go back to f sub x, the first partial with respect to x, and take the derivative with respect to y. So the derivative of 2x with respect to y is 0, plus the derivative of y is 1, minus the derivative of 3, which is 0. So the second partial, mixed partial, is 1. All right, step 2 is to find the solution to the system of equations, partial with respect to x equals 0 and partial with respect to y equals 0. So we have to find a point that makes both of those true at the same time. So let's set that up. 2x plus y minus 3 equals 0, and x plus 2y is equal to 0. So our two strategies here are either elimination or substitution. I'm going to do substitution. So I'm going to solve this second equation for x. So subtract 2y from both sides, and I get x equals 2y. Then that I'm going to take and substitute in here for x. So when I do that, I get 2 times, replace x with negative 2y, plus y minus 3 is equal to 0. So negative 4y plus y is negative 3y minus 3 is 0. And add 3 to both sides, divide by negative 3, y would have to be negative 1 to make that true, right? Quick check. Negative 3 times negative 1, 3 minus 3 is 0. So that works. Okay, so we've got part of our solution. So what we're going to do is we're going to plug that into here. So x then would have to be negative 2 times the y value that we got, so negative 1. So that means 2. So we have a solution is x is 2 and y is negative 1. So step number 3, calculate d of 2 comma negative 1. And let's recall that that's the second partial with respect to x at that point times the second partial with respect to y at that point minus the mixed partial at that point, and then squared. And this case, though, if we go back up to all of our second partials, notice they're all constant functions. So f(x)(x), no matter what x and y values we have, this is always 2. And f(y)(y) is always 2. And minus the mixed partial squared, so minus 1 squared, so this is 4 minus 1 is 3, which is positive. So D being positive tells me we either have a max or a min, and we have a max or a min by looking at the second partial, right? And if that is positive, that means concave up, we have a minimum, or if that is negative, then we have concave down, essentially, and then it's a maximum. But f of x, the second partial with respect to x, is 2, so that's positive. So kind of think, right, positive means concave up, so that tells me we have a minimum at the point 2 comma negative 1. Okay. And if you're interested in seeing what this looks like, it's pretty easy. You can graph this in like Wolfram Alpha or GeoGebra.org. You can Google 3D graphing, and lots of options come up, and you can graph that up, and you'll see that basically this looks kind of a strange function. Kind of looks like this. And so here is our minimum point that we've got here. So kind of sort of looks like a cone shape sort of thing. Okay, it looks kind of like that. All right, let's try another. All right, find the relative extreme points. And of course, there may be a saddle point. You can find that along the way. For G, G of xy equals x cubed plus y squared minus 3x minus 4y plus 3. All right, so first steps, we need our partials. So the partial with respect to x is 3x squared plus 0 minus 3 minus 0 plus 0. Partial with respect to y is going to be 0 plus 2y minus 0 minus 4 plus 0. Then we need the second partials. So the second partial with respect to x is going to be 6x minus 0. Second partial with respect to y is going to be 2 minus 0. And then our mixed partial, g x y, so the derivative of g sub x, the partial with respect to x, with respect to y. Well, there are no y's in there, so that's basically treated all as a constant, so that is actually 0. All right, so step 2 is we need to solve the system of equations. G sub x is 0, g sub y is 0, right? So let's set that up. 3x squared minus 3 equals 0, and 2y minus 4 equals 0. Okay, well notice these are, like the first one is independent of y and the second one is independent of x. So basically what we're going to do is solve each of them separately. Right? So this says 3x squared must be 3, so that means x is either going to be 1 or negative 1, right? Because you get x squared equals 1, so x is negative 1 and 1. And then this one we solve, let's see, 2y would equal 4, so that means y is equal to 2. Okay. So this basically means we have two solutions here, because we have the case when x is 1, and you have case when x is negative 1. But no matter what the x values are, the y value, we get only one y value. So we actually end up with two solutions here. So we have 2 points to consider. So we need to calculate d for each of them. So I'm going to give myself a little bit of room here. So d of 1 comma 2 is second partial with respect to x of 1 comma 2 times second partial with respect to y, 1 comma 2, minus the mixed, oops, these should be g's, right, not f's. This is the function g, we're not using function f. Sorry, let me fix that up for you. All right, so g xx, g yy, and g xy at 1 comma 2 quantity squared. Okay, so g xx is 6x. So this is going to be 6 times the x coordinate, so that's 1, times g yy is just plain old 2, and then minus the mixed partial, which is 0 squared. So this is 6 times 2 is 12, and so this is positive. And since it's positive, then we also have to check fx, or g, I keep doing that, gxx. So gxx at 1 comma 2 is 6 times x, so 6 times 1, which is 6, which is positive. So again, think positive, second derivative, positive, concave up. So we have a relative minimum at 1 comma 2. Now we need to check d at negative 1 comma 2. So let's see, that's g of xx at negative 1 comma 2 times g y at negative 1 comma 2 minus g of xy at negative 1 comma 2 squared. So g of xx, that's the 6 times x. So 6 times negative 1 times gyy is always 2, so times 2, minus our mixed partial squared, so 0 squared. So this is negative 6. So that's less than 0. So if we go back to our conditions there, remember if d is negative, then we have a saddle point at negative 1 comma 2. Okay, so we have a relative min at 1 comma 2 and a saddle point at negative 1 comma 2. Okay. All right, one last example, and this is an applications problem, and we're going to be looking at how many types of each widget do we need to sell in order to maximize our profits. So a company sells widget A and widget B, and they sell X thousand of widget A. So X is going to represent the number of items of widget A, number of units of widget A that we're going to produce and sell. And then we have Y thousand of widget B. So Y represents the number of widget B that we're going to produce and sell. And we have a revenue function, and we have a cost function, but we're asked to maximize profit. So we have to remember that profit equals revenue minus cost. So in this case, our profit function is going to be 17x plus 21y, and then we subtract off all of our terms in C. So it'll be minus 4x squared plus 4xy minus 2y squared plus 11x minus 25y plus 3, right? So if I'm going to subtract off the constant, or the cost function, it means every term in here gets subtracted off, so it means every term gets an opposite sign. So before I move on, I want to collect my like terms. So let's see, I have a term that has just an x in it. There's another one that has just an x. Do I have just a y? I sure do. Just y and just y. And then I have an x squared, no other x squareds, a y squared, no other y squareds, and a mixed xy. So let's see. So p of xy is 17x plus 11x, that's 28x. And 21y minus 25y is minus 4y. And then minus 4x squared plus 4xy minus 2y squared, and then plus 3. Right? So this is the function that we're looking to find the maximum of. So our profit function is that function there, and we're going to need to find the maximum. So it's the same process. So first step is I need the partials. So p sub x, let's see, derivative of 28x with respect to x is 28. Minus 4y, that's going to be, the derivative is going to be 0 because it doesn't have an x. And then minus 4x squared is going to be minus 8x. Plus 4xy is going to be, derivative of 4x is 4 times the constant y. Derivative of minus 2y squared is 0. Derivative of 3 is 0. So there's our partial with respect to x. Now we need our partial with respect to y. Derivative of 28x with respect to y is 0. Derivative of negative 4y is negative 4. Derivative of negative 4x squared is 0. Plus constant 4x times the derivative of y, which is 1, so just 4x, and then minus the derivative of 2y squared, which is 4y, and then plus the derivative of 3, which is 0. Right? And then we need second partials. So derivative of that with respect to x is just going to be 0 minus 8 plus 0. And second partial with respect to y is going to be 0 plus 0 minus 4, and then we need our mixed second partial. So we go back to here and take the derivative with respect to y, so 0 minus 0 plus 4, so we get that. Okay, step 2 is solve the system with both partials equal to 0. Okay, so let's write that down. So we've got 28 minus 8x plus 4y equals 0, and negative 4 plus 4x minus 4y equals 0. So now on previous problems we used substitution, or in the case of the other problem, like each equation was only with one variable, so we could solve them separately. So notice here both equations have both variables, but instead of doing substitution, I want to notice that I have plus 4y here and minus 4y here. So what I'm actually going to do is what's called the elimination method. Is I'm going to add these two equations together, and I'll end up with an equation in just one variable. So let's see, add the constant terms together. 28 and negative 4 is 24. Negative 8x plus 4x is minus 4x. 4y minus 4y is 0, and then equals 0 plus 0 is 0. So we end up with that equation, which we can then solve for x. So 24 equals 4x. So x would have to be 6, right? Okay, so that's one solution, 6 comma, or that's half of the solution. And then we just need to find a y value. Well, I can pick either of the two equations and solve for y. So I'm going to plug this into 28 minus 8x, so 8 times 6, plus 4y is equal to 0. So this is 28, 6 times 8 is 48, plus 4y is equal to 0. So negative 20 plus 4y equals 0. So y would have to be, add 20 to both sides, divide by 4 is 5. So we get the solution 6 comma 5. Right? Now, just like before, you can't just assume this is a maximum. You have to prove that this provides a maximum. So that means we need to find d of 6 comma 5, which means second partials at 6 comma 5 times the other second partial at 6 comma 5 minus the mixed partial at 6 comma 5 squared. Okay. All right. Second partial with respect to x is negative 8 times second partial with respect to y is negative 4 minus the mixed partial, which is 4 quantity squared. So negative 8 times negative 4 is 32 minus 16, which is 16, which is positive. Okay, good. We'd be really upset if this was a saddle point, if that came out negative. But what we need to check now is the second partial with respect to x, which in this case is negative 8. So again, think second derivative negative means concave down. So that does indeed, we need a maximum. So they would need to sell 6,000 of widget A and 5,000 of widget B to maximize profit. Okay. And that's pretty much it. They all kind of work the same. You just have to do the interpretation here at step 4, right, which we didn't really write in. Step 4 here is if D is positive and the second derivative with respect to x is positive or negative, then you have a max or a min.